Welcome everybody to the Boundary Layer Seminar of Arianna Jordan. Arianna is a third-year PhD student in the School of Meteorology. She got her undergraduate in meteorology at San Jose State and then a master's at Howard University. And she's working with me and Elizabeth on the AWAKEN project. And she's going to give an update on some of her work today. Take it away.
All right, thank you, Petra, for that introduction, and thank you guys for showing up here online or in person. So yeah, as Petra said, I'm going to talk about some recent developments that we've had on this project pertaining to my PhD research, the American Wake Experiment, or AWAKEN. So we deployed about a couple months ago, and we've been collecting data since then. So I'll give an introductory look into that. But first, to start off, let's start with the basics. So if you study boundary layer, you know this figure like the back of your hand. But if you don't, this is the diurnal cycle of the planetary boundary layers. So when I say boundary layer, I'm referring to the lowest few kilometers of the atmosphere that have a direct interaction with the Earth's surface in some ways. So for example, convection that later causes precipitation. And during the day, this heat from the sun causes turbulent mixing in the boundary layer. So that's why we call it during the day the convective boundary layer or convective mixed layer. But as the sun sets, that mixing begins to subside a bit. And so that then leads to a stable nocturnal boundary layer. And then the previous day's convective mixing kind of becomes detached from the surface and turns into this residual layer. Then when the sun rises again, we have that stable layer kind of shift into this entrainment zone, and the mixing starts again from the sun, and then that cycle starts over. So that's kind of the idealized image of the boundary layer, but now we have a non-idealized image with these wind turbines present. And so if you look at these spinning rotors, you can imagine that they might disrupt the atmosphere in some way from this idealized conditions I talked about. Well, first of all, these turbines aren't to scale. The actual turbine's height is usually about this tall, but even at this height, they can still cause some atmospheric impacts on our boundary layer. And these are just a few studies that are naming some of those impacts. So we can have wind speed deficits up to 9%. We can have enhancements in vertical mixing and increases in land surface temperature at night. We can also have decreased wind speed and increased turbulence, and that specifically is known as turbine wakes. And the evolution of these wakes is highly dependent on the boundary layer stability. So these are studies that have come from either wind tunnel experiments or field campaigns or large eddy simulations. So there's been a lot of work done on wind turbines, but there's still a lot that we don't really understand about them. So there's still plenty to learn going forward. For example, there's been a lot of recently built wind farms in the past 20 years or so. There's been a lot of advancements in instruments such as clamps, which I'll be talking about in a moment here, as well as methods to apply the data from these instruments, which I'll also discuss. And there also hasn't been a ton of field campaigning in Oklahoma regarding these wind turbines. Like here's a picture of one here from northern Oklahoma. And it's a really unique land because not only does it have really flat topography, so that helps take away some of the complexities, but we also have what's common nocturnal low-level jet in our overnight hours. That's really characteristic to our region. So there's still a few things that we can learn from all of this. So you might be saying, okay, Arianna, well, why is this important? Why do we care about turbines? Well, they're important from a standpoint of if we understand the impacts of the atmosphere, we can help in the realm of forecasting, including severe weather. We can also better understand how pollutants in the atmosphere is transferred via the exchange of the wind turbines. So that'll help from an air quality stance. And then also we can have a more realistic depiction for numerical modeling inputs. And wind farms are continuing to expand as we shift to a more renewable energy future. So having that understanding now is going to be very good for studies going forward. So with that in mind, let's talk about some of the kind of methods that we can use to observe the boundary layer in general. You could do so with meteorological towers that have instruments on them, radiosondes, aircraft, and uncrewed aerial systems such as drones. But what I'm going to talk about today is remote sensing, specifically the remote sensing capabilities of the Collaborative Lower Atmospheric Mobile Profiling System. Did it without looking, otherwise known as CLAMPS. So we have two systems here, CLAMPS 1 and CLAMPS 2. They've been developed by the National Severe Storms Lab and University of Oklahoma. And here's kind of a model look what they look like if you haven't seen them before. But both of them contain a halo scanning Doppler lidar to be able to collect kinematic data, so wind speed, wind direction, vertical velocity. They have an infrared spectral radiometer, or ARI, so we can collect thermodynamic data of water vapor or temperature, etc. And they also have equipped a microwave radiometer, so we can get surface observations of both kinematic and thermodynamic data. So these two platforms have gotten a lot of use this past year, being out in various field campaigns. And currently, they are out in another one, which I will introduce as AWAKEN. So the American Wake experiment was designed, it's an initiative targeted at studying observations relative to wind farms. And the overall purpose was to understand wind turbine wake interactions, which, if you remember, wakes are decreased areas of decreased wind speed and increased turbulence. And those can kind of cause stress on the turbines and fatigue them. So this project was kind of made to better understand that and ways to maybe mitigate that for a longer lifetime. So there's been a lot of really interesting research questions. So if you want to check it out, you can take a picture of this QR code and it'll bring you to the main website. But for our purposes here at OU and Lawrence Livermore National Laboratories, who we're closely collaborating with, we want to investigate wind farm impacts on the boundary layer the way some of those previous studies on my first slide have done, specifically using remote sensing approaches from the field. And so we deployed this past October, and the campaign is planning to go for about a year into September next year. But we deployed in a collection of wind farms that are kind of near Enid, Oklahoma, here in northern Oklahoma, if you look at this map denoted by the green star. So there's a collection of wind farms out this way. And so let's take a look at some of those wind farms. So here's a zoomed in image of this map that we saw. Here's the green star denoting Enid. And what you're looking at here is the US wind turbine database from the US Geological Survey website. And these little dots that you see are representative of wind turbines, or specifically in clusters, wind farms. And so these colors that you see are the height, are referred to the height of the wind turbines, which are kind of in this color bar here, but the darker orange colors are supposed to be the taller ones, and then the yellow ones are slightly shorter, and then the gray ones are shorter than that, etc. What's also cool is we can see the progression of how they were built from 1980 to present day. So I'll loop through that right now. So the dates are here, but if they're hard to see, it's during 2000 that the wind turbines really start to come up. And then by 2010, it's when they really start taking off. So it kind of drives home that point of they're not only expanding, but they're expanding really rapidly. So I'll let that come through again. So yeah, we have a lot in this area. So it ended up being a good, sufficient area for deployment. So we're going to talk a little bit about CLAMPS deployment at the AWAKEN site. And so last year we did a few site visits to take a look at this area and see where would be suitable places to place clamps and collect these observations. So we decided on these places that are denoted by these white pins. And so looking at Clamps 1, we found this place, we found a golf course to put it at, specifically called Rolling Meadows Golf Club. And the reason we picked it is, as you can see, it's surrounded by wind turbines. So it's a really nice place to get that data pretty much everywhere except the west. But it's also really great because there's favorable terrain, so not too much vegetation cover in this area. And there's plenty of power availability for clamps from the golf course. Initially, we were a little bit concerned about golf course irrigation that might happen, but that was before we really saw the site. And it turns out the land is actually not too different from the land surrounding it anyway, which is crops. So as far as land heterogeneities go, that's not too much of a concern. Clamps isn't located directly on the golf course, but a little ways off of it. But we did see a few golf balls like around the area we put it. That said, the times we've gone up and checked on it, there hasn't been any damage that we could see. So that's very good. So we have this nice place for Clamps 1, but we also wanted data outside of the wind turbine influence so we could compare it well. So for Clamps 2, we decided on this location, which is the atmospheric radiation measurement or ARM site, E36 to be specific. And the reason this place was picked is because it's pretty good, a pretty good area outside the wind turbines. There's favorable terrain here too, so not too much vegetation cover. And as we go further, I'll show maps of that so you can see. Power availability is here too for the ARM instruments, so we could use it as well. And it also is a nice place that allows for north-south transect if we wanted to do that. The main consideration here is there is this red dirt wind farm that's a little to the southwest that we wanted to be cognizant of in case there is southwesterly flow. But luckily it's a pretty good distance away that we felt comfortable enough to place clamps here. But just to get a little more, just to make sure it's not too close for comfort, here's also some climatologies of wind roses that were taken at the main ARM central facility. So Clamps 2 is at the ARM site E36, and up here is the main ARM central facility for the Southern Great Plains. So that's where these wind roses come from. And what you can see here is the average wind from at 90 meters and 500 meters from 2013 to 2019. And we can see it's mostly predominantly southerly flow, especially at 90 meters. At 500 meters, there is a little bit of southwesterly flow too, in the upper levels. Regarding the red dirt wind farm, you have to go pretty far to the southwest to get a directional influence, but overall, it's not as much of a concern for most days based on this climatology. And then these wind farms are for October, November, December, which are the dates of interest so far during this time period. And they show pretty similar results, except for December, which has a little more northerly wind flow. So that'll be something to consider in case we do get northerlies. Then we can also get an influence from Armadillo Flats. So that's something to consider, but overall, the deployment spots we're pretty happy with. So we have our spots. Now we can look at a test day of data. So here are the results from the day of October 21st, 2022. And this is primarily just looking at the lidar data. So we're just looking at horizontal wind direction, wind speed, and then vertical velocity from both Clamps 1 and Clamps 2. So just focusing on wind direction, we can see that the winds are predominantly southerly throughout both the Clamps 1 and Clamps 2 time period. In Clamps 1, there's a little bit of blitz, so maybe more southeasterly flow, but overall, southerly flow. And then going to the wind speed, we can see what you can see here is a defined low-level jet. And what's really interesting about the low-level jet here is it's very elongated. So if you think about the timing of the nocturnal hours, 0Z is 7 p.m. And then let's say 12Z, that's about 7 a.m. So the nighttime hours you'd expect to be you would expect the nocturnal low-level jet to be more so in this area, but it actually goes through all the way through the morning hours, and even the max of the jet is through the morning hours. So that's something that's pretty interesting that we do see in both cases. The lidar beam doesn't collect the top of this layer as well as the clamps one site, but we see those very similar nocturnal low-level jets that are really long. And then we get the mixing during the day. The real story here is the vertical velocity mixing. So for clamps too, outside the influence of the wind farms, there's a little bit of mixing happening at night, but it really increases during the day when the sun heats up. At 20Z, there's this lot of really vibrant mixing happening. So quite a bit of turbulence here where there's the decreased wind speed. But overall, this is kind of a typical profile that we would expect for the Oklahoma region during this time, seasonally. The Clamps 1 lidar, however, is a lot different than Clamps 2, where there's there's an updraft mixing happening at night in two specifically separate areas. And then during the day, we have this larger area of mixing. So going back to these nighttime areas, we had a little bit of discussion about what could be causing this. If you look back at the wind speed around these times, well, to start with the first one, you can see kind of these streaks that are going down kind of diagonally. And those are what are called diagonal striations. So this is supposed to kind of help see it. It doesn't really a lot, but you can still kind of see the lower wind speeds there. So what these are basically when the maximum velocity descends really quickly towards the surface with time. And so we're thinking maybe that possibly had an influence around this time period where it's really prominent. And then looking at the second blip, we talked a little bit about what's called an upside down boundary layer. And so what this is basically where the main source of turbulence is actually elevated near the nose of the jet, because this blip happens kind of where the low-level jet starts to rise up again. And so it's interesting because instead of being turbulence near the ground, it starts elevated and then it mixes down. So that's also a theory we talked about, but the thing is it doesn't really explain why there's primarily updrafts in the atmosphere. You would expect maybe downdrafts in that case. So there also is a diagonal striation here as well. That's actually quite easy to identify, or easier than here, I should say. And so it could be a mix of maybe those processes happening, like maybe that right after the other, causing the turbines to, or picking that up. And so we do have these features to these diagonal striations in the clamps too. It's harder to see, but there are a little diagonal striations there. So the features are the same, but what's different is the wind turbines are in this vertical velocity. And if you look kind of at the 0.2 kilometer range, you see there's kind of this increased area of mixing, and that would be where the wind turbines are located. So there's still a lot of questions, but it's a really interesting case just from this one day. Okay, so moving forward, going forward into the campaign, one goal from AWAKEN is to retrieve height estimations of the diurnal boundary layer. And so if you saw my seminar last year, I talked a little bit about different height methods that you can do to retrieve these estimates. But for this talk, I'll focus on one mainly that specifically targets observations from clamps. So that refers to a composite fuzzy logic algorithm that was developed by Bonin et al. 2018, and it employed Doppler lidar measurements. So what fuzzy logic is it assigns a measure of truth to conditions as opposed to binary true or false from Boolean logic. And so my advisor, Dr. Smith, has a really good analogy for this that I'm going to steal because it helps me understand it. So you can think of it like a car coming to a stoplight. Basically, with Boolean logic, it's just true or false. And so if the condition is the stoplight, the car is just going to go whoop, stop immediately when it gets to that condition. But with fuzzy logic, degrees of truth are input into the fuzzy logic. So it's like the car is gradually stopping to the stoplight. So fuzzy logic is the good driver. So you can think of it like that. And in terms of height detection, we can employ this fuzzy logic kind of concept. So these are the steps to do that for height detection. You can fuzzify by passing the input through membership functions assigned either to 0, which means they're a member of the class, or 1, not a member of the class. And then you can aggregate these values by taking the mean, the weighted means of them, which in this case is equal to 1. And then the first output level that is less than or equal to 0.5, which is the set threshold, is the first height of aggregation for the height estimate. So that'll be our first height. And then you can do it again to receive a second aggregation, or even multiple times to receive a more refined height estimate. And so Smith and Carlin et al. 2022 employs this method, but also adds thermodynamic profiles from clams to get kind of a weighted function for the buoyancy-driven characteristics in boundary layer transitional periods. So the reason I'm talking about the fuzzy logic is because this is something we really want to employ for AWAKEN going down the road, but it's something that's already been done for a previous campaign we worked on. So, and understanding those results can help us with coming up with an expected height for AWAKEN cases. So with that, I'm going to introduce the Blissful case. And this campaign took place last year. Some of you were a part of it. But it lasted about a month in the summer of 2021. And it took place at OU's Kessler Ecological and Atmospheric Field Station, so a little down south from where we are in Norman. And so we're taking Windfarms out of the equation for right now. But what Blissful was meant to do was to kind of test the clamp systems and make sure they were doing well for these campaigns that we did all of this year. And then also it enabled the training of students and early career researchers. And so for Blissful, both clamp systems were also used like AWAKEN, but here they were co-located, as you can see by this map of the CAF site here. And so we did this to allow for different scanning strategies of the lidar systems. So for the CLAMS 1 lidar down here, we decided to employ high resolution vertical velocity data. So we can get high resolution turbulence readings. And that in turn produces low resolution wind speed and wind direction data. Alternatively, with the CLAMS 2 lidar up here, we did the opposite, where the high resolution is actually with the vertical azimuth display, or VAT scans, which produce the wind speed and wind direction. And then that in turn lowers the resolution of the turbulence data. And so with all that in mind, here's an example of the second generation aggregation height estimate for the day of June 18th, 2021. And so you can see the reason I overlaid vertical velocity was because it very much aligns, the height aligns very well with the vertical velocity, and it even dips in places where the turbulence dips as well. So during the daytime, the height estimate coordinates very well with the mixing that happens in the atmosphere, and then there's obvious drops where you see that. So that's one of the results that we got for Blissful. And then so this CLAMS fuzzy logic height estimate is based off of different types of data from both CLAMS 1 and CLAMS 2, but we weren't initially sure what would be the best combination, like high-res vertical velocity stairs or the high-res VADs, et cetera. So we did a combination of all of that, and here's the results of that. So this is the high-res turbulence and high-res wind speeds together. This is high-res turbulence and low-resolution wind speeds in here, and you can see there's not much of a difference. But when we take out the high resolution turbulence and take and input the low resolution clamps 2, you can see that the height aggregations is a lot noisier and has a lot more uncertainty in figuring out where the height estimate is, as opposed to like over here where it doesn't have this giant dip here. And then the same kind of result for when both data sets are low res. So what's nice or what's good about this is it really brings home the point of how vertical stairs data, at least in this case, seems to produce really good height estimations, even if there's low res wind speed data input. Whereas even with high res wind speed data, if we don't have high resolution turbulence data, it's going to be a lot noisier and more uncertain of a height estimate. So using that information, we can move forward into what we would expect as a height input for AWAKEN. So this is just to compare the blissful June 18th case that we just saw with the AWAKEN clamps 2 case that we saw a while back. So this is still keeping wind farms out of the equation. Just for the sake of comparing the topography, this is what the CAF site looks like. So there's these trees in the southwest area of CAFs, and there's a little bit of rolling hills in the area too. So that's something to keep in mind for a southwesterly flow. For the AWAKEN site, it's very flat, not a lot of trees, except for tiny groves of trees around. So it's a lot more secluded. And both of these areas are probably have more brown grass because it's a fall area. And so given that Blissful and AWAKEN are taking place at 2 different times of the year, it was kind of hard to find cases that were similar to compare. But that said, these are the synoptic properties of both those days, and both are under high pressure. Their maximum temperatures are actually not too different. The October case was still at about 85 degrees, while in June in 2021, it was about 90 degrees. So it's really the minimum temperatures at night where it drops a lot more in October. But clear days, I didn't show the visible satellite here, but both days were clear, and there's maybe a little bit windier conditions aloft for October because of these tighter contours, and we're devoid of rain. And then there's this mess happening out here that that's not in our area right now, so we're just going to ignore that. But so here's the comparison of Blissful and the AWAKEN clamps 2 case. So for Blissful, we have these very southwesterly winds during the night when this nocturnal low-level jet is happening, but then they shift more southeasterly during the day, whereas clamps 2 is predominantly southerly, except for maybe this elevated southeasterly flow. And then what I liked about comparing these 2 cases is both had the nocturnal low-level jet kind of in the same places, except this one in October is a lot more elongated. And then it's really in the mixing profiles that you can see how deep the profile is in June, because we have way more heating from the sun compared to the October case. So because we found that the stairs are the height estimate is highly dependent on the stairs data, the height estimate I personally drew out depended very much on that stairs data. So that's what I estimated as a height, where I kind of really make prominent dips here. Maybe they wouldn't be that prominent, but that's what I would. My estimate is based a lot on the stairs data. And now we can add in the case with the wind farms. So this is what the golf course looks like where we deployed clamps 1. You can see it here. Here's the golf course. And there are some bodies of waters for the golf course, but otherwise there's not a ton of terrain influence complexities otherwise. And so now when we add this clamps 1 case, we would expect, or the resulting height estimate I added is also very dependent on the stairs data, which which you can see it gets up to even higher heights, even the same as the blissful case. And so so the way I was thinking of it was if it was the VADs that I was dependent on, then the clamps 2 and clamps 1 height estimations would probably be more similar. Maybe it would be a little lower in this clamps because of the lower resolution, but because the stairs, because it performs so well with high-res stairs data, I also depended my height on that. As far as the nocturnal mixing goes, it's difficult to kind of measure the nocturnal properties of the boundary layer, but I did add maybe a little bit of a higher heights in these areas, just in case, even though in the blissful case, it isn't really clear that that's what's causing maybe this elevated area. So all that said, concluding remarks. So the wind turbine environments do yield some really interesting results in the vertical velocity features. And we can see in the wind speeds that there are diagonal striations, and there might even be an upside down boundary layer processes happening. We kind of need adequate turbulent kinetic energy measurements to really be able to make that claim. But that's something that we can look into as we go forward. And then also the fuzzy logic method for height estimation strongly depends on high resolution vertical velocity data, at least, and in this case, we can get the resolution up to 1 second. And so that's also why kind of for AWAKEN, we set those resolutions to be really high in the turbulence. However, it's possible that this wouldn't be the case if there's the presence of non-turbulent motions, as seen from Bonin et al. That developed the method, such as gravity waves. So that would be something interesting to see if those features do come up. And then as far as future work goes, there's a lot of future work to be had because we just started. But for the daytime boundary layer, there's a lot of turbulence studies we can do going forward as far as evolution and comparing the ratio of mechanical and thermal turbulence. In the nocturnal boundary layer, we have the nocturnal low-level jet cases to look at, which we already have an interesting one here. As well as mesoscale disturbances like gravity waves and bores. We can also look at the entire diurnal cycle of the boundary layer and look at height analysis like I presented here. Convection and convection initiation from before the turbines were built to after, like in that map we saw. Storms, if there's any modifications to storm outflow, as well as even from a modeling standpoint, looking at lidar scanning simulations. And then also we can look at the day to evening transitions, since there's a lot of work to be understood about the transitional parts of the boundary layer, such as the timing and the relation to the nocturnal low level jet, like in this case. Okay, so I might have gone a little overboard with the acknowledgements, but I just want to thank my advisors, Drs. Petra, Klein, and Elizabeth Smith, as well as Dr. Sonia Wharton, who helped a lot with deployment at AWAKEN. My committee members for sticking with me as we at last start to get this data in. All AWAKEN project managers and collaborators, and my friends and family, as well as my four-legged godchildren over here. None of these are my pets, but they basically are. So with that, that's my references. And if there's any questions, and here's this QR code as well. So thank you.
Open questions in the room. Also, opening questions in the chat as we speak.
Yes.
What are your thoughts? Why do you think the boundary layer height is higher at water, the outside or inside the wind farm?
You mean during the day when it like peaks like that? I think that's a result of both the wind farm mechanically mixing and then the thermal, in addition to the thermal mixing. So what I haven't looked yet, but what I'm thinking is maybe the hottest part of the day happened when near the end of the day where it kind of rises like that. And so I think just with that mixing, we see it a lot more during the daytime. And so it's really evident there. I would have to look and make sure that that's what's happening, but that would be my guess.
Maybe just to follow up really quickly, are you concerned that maybe or do you have to be concerned about the sensitivity of the lidars, since you have two different lidars? And if the boundary layer height estimation is very, very much dependent on the vertical velocity data, the range could play a role as well, right?
Yeah, that's something to definitely consider. And that's why it was nice for Blissful to have it co-located, so you can kind of see how that data compares. So I think that would be a good campaign to look back on and see if those differences are really major or not, and then kind of determine if the heights are doing those differences. Anything else? Cool. Thank you, guys. Oh, no. Oh, okay.
So she says, do you think the collective data I wanted to get robust statistics compared to turbulence across the two different sites? If not, how will you address this for isolating the wind effects?
That's a good question. Yeah, so one thing speaking of which, that I do want to mention is co-located with the clamps systems. We have profiling lidars that are supplied by Sonia and her team. So that also will help get some even more wind measurements that we can look at. So we've been downloading that data too. And so that'll help as far as comparison and making sure that the data that we're getting is viable. But we can also look at statistically use that data as well, and kind of get those measurements to understand that. As far as if it'll be enough, so these systems are only going to be here until December, and we're actually going to shift into a more mobile mode next year. And so that'll give us the opportunity to collect even more data in more areas, and in case it isn't enough. So that would be something to look at like before we do that, and make sure that that we need more of that statistical data, if that makes sense.
About the extended facility sites available from the ARM facility. You could use those sites as well.
Yeah, absolutely. So if you go back to where the ARM, where the ARM central facility is located, it's really close to where clamps 1 and clamps 2 were. So it would be, of course, it's black. So yeah, it would. That also provides plenty of measurements. If you don't know, the ARM facility collects continuous atmospheric measurements, similar to what we're doing here, but even more in terms of meteorological towers. They launch radiosondes. They have a lot of different data that we could use as well. So that's also a good resource, and that's one of the reasons too why we deployed around here. And we have more sites as well. There's this as an extended site, and then there's sites to the west and east. So they also provide more measurements that you can look at.